This next video focuses on the LEDs class. This initially was adapted from a similar class by 6328, Mechanical Advantage. It's changed a bit since then. Um, the LEDs class is technically a subsystem, um, but we don't really use it that way in many ways. Um, it follows a slightly different model. But it does extend subsystem base. Um, but it doesn't have the whole IO layer and the same approach, really, to be honest. It is a singleton class. Various other code and other subsystems need to grab a reference to the LED subsystem to request different states. So it's got its get instance method here. Um, Technically, 3061 lib supports the candle and the Rio. We haven't used the candle in many years. We only use the Rio, and so um, prior to 2025, we would use robot config to determine which type of LEDs were on the robot. But now it's actually hard coded, as you see here, to the Rio. This could certainly be changed to the candle. We do that so that we can start interacting with the LED subsystem before robot config has been constructed. That gives us the ability to have the code loading pattern that I referred to back in when we reviewed the robot and robot container classes. So that's a little bit of the why behind why it's hard coded and structured that way. Um, one neat change that we've made over the last few years is to use tree sets to prioritize LED states, and this was inspired by a post on Chief Delphi of how 6995 uses tree sets. And so the way this is structured is, I guess we have several tree sets here I should comment on a little bit. Our LEDs are designed to be able to control just an entire strip with a given pattern. Also designed to be like mirrored left right, like maybe you have a strip. It's one electrically connected strip, but you have one on the left side and the right side. We also have the ability to have um, a static portion of the LED strip with low, middle, and high regions of that strip, and then a shoulder as well. And the shoulder would be, often think of wrapping LEDs up along some vertical member and then across horizontally. The horizontal part we would refer to as the shoulder. But all of that's configurable, so you can just use all the LEDs at once or break it down into regions so that multiple things can be communicated at the same time. But that's why there are so many tree sets here, and we'll see later how that's used. Um, Here's the enumeration of all the different LED states. And the way this works is that each state has a little lambda expression that tells LEDs, um, the LED subsystem, what pattern to display. The order of the states in this enumeration is the priority order, and therefore the first state is the highest priority state. What that means is various subsystems, other code may, within a single periodic loop, multiple places may request an LED state. The one that gets displayed is based on which one has the highest priority. So, for example, no matter what code is requested, what LED state, if we are e-stopped and the e-stop state is requested, that will be displayed on the LEDs because it is the highest priority. So you can see our priority order here, and these can certainly be adjusted around for different priorities. So we have things like e-stop, fallen. We have an auto fade. This came from 6328, where at the end of auto, there's an LED pattern there to signify that. We have a low battery one. Um, we have a different, if we're in demo mode, we have a different, and we're disabled, we have a different LED pattern than we would at a competition. We added this one in Reefscape, no auto selected, so that if an auto routine is not selected, um, we get the solid yellow, which reminds the driver and operator to select the auto for the match. Um, Disabled patterns, auto patterns. We have an alert here at the end game, so a little strobe when we get close to the end game portion, so the driver knows it's time to do whatever needs to be done at that point. We refer to some of these in some of the other videos, like the elevator being jammed, ejecting a game piece, releasing a game piece, drive to pose things here in terms of auto driving to pose, being at the pose, having drive to pose canceled, having a game piece, indexing a game piece, waiting for a game piece, um, all of that. So those are all the states. Um, Kind of cool. Um, so the way this works, there's some state tracking that the LED subsystem itself needs to do to keep track of things in terms of like auto and enabling and things like that. Um, a lot of these constants are just constants for the various patterns. Um, let's see, we're not going to go through all of those, but a couple of the interesting things. Here's the constructor for the LED subsystem. You'll notice what it does right away is it creates a thread, little notifier here, um, that does the breath pattern with white, um, and just keeps displaying that pattern for a while. And this runs every 20 milliseconds. This is just to let us know that, hey, the code is loading. Um, Classes are being constructed. The robot will be ready eventually, but I find it very reassuring. Um, Here's the method that other code and other subsystems call when they want a new state. They invoke the request state on the singleton LED class, specify the state they want. It gets by default added to the full states um, tree step. Okay. There is also a request state where you can specify a section. Um, and then it will get added to the appropriate tree set. So this is if we're doing something more sophisticated with LEDs, and we want to be able to target, well, this is the requested state for, um, could be the full thing, or just the shoulder, or just the static portion, or just the low part of the static portion, or the mid or the high, whatever it happens to be. All right, so those are the methods that other code calls. Here's the periodic method for our subsystem. Um, this basically doesn't update the LED state for the first few cycles. So how many is that? For the first 10 cycles, we don't update that. We display that code loading pattern, um, and we want that to continue until we're more loaded. Once we do finish these cycles, we stop the code loading pattern, um, and then we request the default state by default, which was just, off. We do this first so that there's always a state within the section. Um, and then we will invoke this update internal state, which we'll look at in a moment. I guess let's look at that now. Makes more sense. So here's where we're keeping track of some of the different state things. We need to know whether we're attached to the FMS or not and have been assigned an alliance. So we check for that. We check for whether we're disabled and things. And if so, maybe it was at the end of auto. We have the auto fade thing. We keep track of those times so we can make that start. We check if we're e-stopped. We check if we're in demo mode and disabled. All of those kind of internal state to the LED subsystem. Once we do that, the LED subsystem may have requested some states, other code may have requested some states, and so now we determine how to set the LEDs. And so the way we do this is we we check if a state has been requested for the full LED strip. Um, and if so, um, we grab the highest priority one there. So you can see we're calling first there. Because it's a tree set, it'll be stored in sorted order. So this will get us the highest priority state. And then we change the LEDs and log it just so we know where we're at. If full states is empty, then we're just using some other portion. So we take care of the shoulder first, um, and then we look at the static states. If static states is not empty, then we do the static portion. If static states is empty, that means we're actually breaking the static down into a low, mid, and high, and so we do all of those. So you can see how this works in terms of priorities. We update the LEDs, and we clear all the tree sets. The idea, the way the LED subsystem works is that at every cycle it starts in the default state, and it's up to a subsystem to request a state. So if we want to stay in a certain state, like waiting for game piece, every periodic loop we need to request that state, and then it gets cleared out. It's not like it remembers old states, because it's not always clear when they need to go away and things like that. So every time we start with a clean, empty tree sets. Update LEDs is our abstract method. So we'll see in a moment, like that's different for the candle and the Rio, because this is an abstract class. We're not going to go through these, but then there's a bunch of private methods for like different patterns, um, solids, strobes, breath, rainbows, waves, fire, orange pulse, stripes, and certainly more could be added. Um, yeah, a lot of stuff here focuses on these constants determine how we break the LED things down into different portions. And you can see where those are defined up at the top of this class, which I kind of glossed over a little bit here. I guess I should be a little bit more explicit because these are things that need to be changed for any given LED strip. Um, First off is mirroring LEDs. This is if you want the LEDs to be symmetric. Like I said before, it's when I was saying it's like one electrically connected LED strip, but maybe on two sides of the robot. You would set mirror LEDs to true. That way, like, the patterns look as they should. Um, and if that's not your LED setup, then, set that to false. This is the length of the actual LEDs. It used to be retrieved from robot config, but now we don't want to wait for that to be constructed when we're loading. So instead, we have that hard coded. So this would also need to be changed for a given robot. Um, we then do, whether we're mirroring or not affects the length, and then the static length by default is half the length, and the static section length is a third of that. All these numbers can be tuned based on how your LEDs are set up on a specific robot. So, I don't really want to jump a lot into this, but here's the subclass that extends the LEDs class specifically for the Rio, where we use a PWM port to control the LEDs, and we use the addressable LED and addressable LED buffer classes from WPILib. It's relatively straightforward here. This is all pretty low-level stuff in terms of updating the LEDs, setting the data in the buffer, um, dealing with the colors appropriately, all of that. So, um, yeah, a lot of this is dealing with different colors and how LEDs expect to be programmed. Possible the LEDs that you might be using might require different values. And so some of this might have to be adjusted, but these work well for the LEDs that we have been using historically. So, all right, that is the LED class.